This is a short video on interpreting pole zero plots, and in doing so I will use this problem, which is from an exam from a couple years ago. It goes through a couple different options. So there's a bunch of pole zero plots down here, and you're asked to match them up. I gave the answers here, and you could just read this, but I'll talk it through a little bit. So minimum phase, what we're looking for there is something that has all of the poles and all of the zeros inside the unit circle. So if you look through here, it's this one, okay? What that means is if we take the inverse of this, the zeros will turn into poles, the poles will turn into zeros. Remember, something that's stable and causal has the poles inside the unit circle. So both this system and its inverse are stable and causal. Then you're asked to identify FIR versus IIR systems. And even though we talk a lot about both in the class, actually in this setting, there's only one FIR, and it's this one. What you can see here, there's 4 zeros going around the unit circle. And hard to read, there's a little 4 there, so showing there are 4 poles at the origin of the z-plane. Remember, there's always going to be, if we count the poles and zeros at the origin, there should always be an equal number of poles and zeros. FIR has this characteristic that that's where the poles are always either at 0 or at infinity. In either case, it works out that if we have a causal FIR, the poles will be here, and because they're in the unit circle, we're guaranteed to get stability if we have a causal FIR. So unlike IIR, where we have to keep worrying about stability, FIR we don't. Everything else here, you can see poles are not at the origin, and so these are all different flavors of IIR, infinite impulse response signals. All right, the next is, this should be omega, constant magnitude response for all omega. That's a characteristic of an all-pass system, and all-pass systems have reciprocal poles and zeros. So here in A, there are poles at 0.5, zeros at 1 over 0.5 or 2. So these are reciprocal, meaning the locations are one over the other. So this is an all-pass. If you work it out, if you went around the unit circle, and if you kind of go through the math we did some time ago, it works out that the magnitude is constant around here. It's not necessarily 1. You can certainly scale this system by a gain factor to make it 1. But in general, it's the correct statement for all passes that it's constant. Here I happen to put everything on the real axis. It would work just as well if I had, if I rotated these so there was like something at 45 degrees in 0.5 and minus 45 in 0.5. Then I would have something at 45 and 2 and minus 45 and 2. All right, the next two are stable and anticausal and stable and causal. So what you may remember is if we're anticausal, the ROC is the inside of the ROC is basically inside the poles, so it'll be inside the in this case, for example, it's whatever is inside this pole. So if we have anticausal systems and we want the ROC to include the unit circle, which is that's the definition of stability, is that the ROC includes the unit circle. If we're anticausal, it means the poles have to be outside, so the ROC is then inside the poles and includes the unit circle. So this one is the only one of that nature. If we look at the others, okay, what's stable and causal? So this thing, stable and causal, means if we're causal, the region of convergence is outside of something, means outside of the poles, because the pole cannot be in the region of convergence. We want unit circle, again, for stable to be the definition there is that the unit circle is in the region of convergence. So stable and causal means poles have to be inside the unit circle. Definitely true here, here, here. This is a mixed case. Here, we already talked about this one. Here we have poles both inside and outside. So this is the case that is not asked about in the list up top of a two-sided function where the region of convergence, if it exists, will be an annulus. It could be kind of the radius of this pole going out to the radius of that pole. If we have that region of convergence, then we could have a stable system. Okay, behaves as notch filter. So there's two notches here. This is, and one of them is kind of a duplicate. Okay, so here's a case where we put zeros right on a particular frequency. So the positive and the negative. We'll zero them out, so that's a notch. As we talked about in class, if you want to have a notch that's not too wide, you can move a pole at the same frequency, but just a little bit inside the unit circle. That boosts the response near the pole, but it's forced to zero here, so you get a very narrow notch. And the same thing at the negative frequency. So this is an IIR notch filter. FIR is basically if you have zeros on the unit circle, that'll notch out those frequencies. So this could be an example of an FIR notch. A bandpass resonator, what we're looking for here, we want poles. Bandpass resonator means that at some frequency, generally not, the highest or the lowest, because then it would be low pass or high pass, but in the middle, we have a pole resonating near the unit circle. So this gets a little more open to interpretation, but here we have poles relatively close to the unit circle. So as we move around, we'll start to really grow our response when we get near this pole, or near this pole, or near this pole. Over here, same thing happens. We have a pole here, so if we move around, our response would go up quite a bit because of this pole. And at the negative frequency matching that, we get the same thing. So these would be the bandpass resonators. Comb filter. A comb filter is basically an FIR filter that knocks out tones and harmonics. So, a notch filter is kind of like a special case of a comb. So this is both a notch and a comb. Here we'll knock off this frequency, whatever this omega-1 and minus omega-1, that pair will knock that off, and then it works out this will be like a multiple, so this would be 2 omega-1 over here. And if we have, you can have a notch filter as we saw in class with many, many zeros around, knocking off a lot of frequencies. In the book they talk about a use for notch filters, in one of the early uses was in analyzing sunspot data, because there's kind of a fundamental and then a lot of harmonics, and you can use a comb filter to get rid of those. Okay, low pass filter, what we're looking for here is something that has a high response near near omega equals 0, which is this point. So this of course is all pass. This, we have a 0, so that's definitely not a low pass, right? Same here. This was a notch. Here, this is a little ambiguous, but here we have kind of a couple poles away from the axis that'll kind of generally boost up the response in this lower frequency region. And then we have zeros over here that'll kind of pull down the response. So this is definitely not a perfect low pass, but it has higher response over here, and then lower response over here. This could be considered as a low pass, kind of, sort of. Finally, what has the shortest impulse response? Well, all of these are infinite, except for this one. So it wins kind of by default because it is finite. So the FIR is, this is another way of asking which is the FIR impulse response.